seconds here. I'll let you know when we're hot.
Okay, sounds good. Are we presenting? Are we broadcasting?
Yes.
Okay.
And you're on camera.
I'm on camera? Okay, excellent. Need to duck down and plug the computer in. And you are recording?
Yes.
Okay. Oh, we should have gotten some grand introduction music, you know, like the Emmys or something. Coming to you live from Maui and other parts of the world. This is the 2021 High Star presentations. Who's with me on that idea? All right. All right, we should begin. This is the 2021 High Star Program presentations. I'm Dr. J.D. Armstrong. So this week we've had several students from around Maui and also some students from the mainland joining us to learn how to do real research in astronomy. And these are their final presentations for that program. Our first group will be on stellar, or will be, let's see, I need to find my notes. There we go. So our first group is Spot the Rotation. They will be discussing solar physics. Their mentor is Ellis Avalon, and the students who will be presenting are Aviva Maisel. Aviva's a first-year student that just graduated from Montessori of Maui and will be attending Seabury Hall this fall. Wilson Chow, who this is Wilson's third year at the High Star program. He's a student over at Maui Waiana. And Peyton Ikeda. And Peyton kind of joins this group in a little different way than most of the students. He's part of the Maui Economic Development Board's STEMworks program and has been working with me, but since I've been running this program this week, he's joined in and really dove into the research. Peyton will be attending Meilani this fall. And so I will now turn the time over to Wilson, Hayden, and Aviva. Are you there?
Hi, JD.
Okay. Oh, wait, just a minute here. And let me know when you need me to change the slide, and I will do so.
All right, thank you. Okay.
No, I'm going to do that. That what you're waiting for? Okay.
Yes. All right, the sun is a star that supports all life on Earth. Other than that, it's a pretty regular star with average mass and magnitude. The sun is the closest star to us and is the star that most affects us. We used it to learn more about the other stars in the universe. Stars are made of plasma, which is what fire is made of as well. Next slide. So solar flares. The sun can undergo solar flares, which is the release of large amounts of energy. They show up as a sudden brightening in the sun's atmosphere. Solar flares can cause damage to satellites by sending particles through space. Solar flares are made from the solar particles that escape through the magnetic field that protects our Earth. The solar particles are then lit up by nitrogen and oxygen particles to make the aurora borealis, which is the northern lights, and the aurora australis, which is the southern lights. Next slide. So sunspots. Sunspots are often the source of solar flares. And a sunspot, like its name, is a dark spot on the sun. Sunspots appear when a very strong magnetic field comes up to the surface of the sun, cooling the plasma and forming a dark spot. We are using sunspots to track the rotation of the sun. Next slide, please. Here's the close-up image of a sunspot. Next slide. So what is the motivation of us tracking the rotation of the sun? Well, rotation is a property of the sun that affects how many solar flares the sun produces. We wanted to test a method that is used to measure the rotation of stars. Sunspots can be used to track and calculate the rotation of the sun. Next slide.
Hi, I'm Peyton, and I'll be explaining the data collection and methods that we use to undergo this data collection. So here you are looking at a GIF of the helioviewer.org. Helioviewer.org is a website in which the Solar Dynamic Observatory uses their instruments and tools in order to capture the surface of the sun and the sunspots on them so that we could observe them and make observations and collect data based on what we saw. It has been around since 2010 collecting this data accurately and available for us to use whenever we need. Next slide, please. Next, we have our data collection. Out of all the sunspots that we collected, here shown is 20% of the data out of the 50. From left to right, I will explain what each of these columns are and why they're important to our experiment and data collection. So first is the Sharp ID, which is how HelioViewer addresses our sunspots and keeps them accounted for. Next in line is our time in and time out in Julian days, which is basically how scientists keep track of time outer space. So time in and time out is basically when the Solar Dynamic Observatory and how the Solar Dynamic Observatory keeps track of the sunspots coming in and out of the field of view. The transit time will be the time that it took to enter and leave the view. And then we have the transit time in seconds, which is basically just the transit time converted from days to seconds. Next is our latitude, or our vertical displacement from the equator. And we have this in degrees, and this will later be important for our data to show why the rotation period changes as a function of the latitude. Next slide, please. Next is our distance traveled. And for these next few columns, we have to use equations. So this first equation used in the distance traveled column would be the circumference equation, which is shown here. It's a modified version to fit our needs. It will be pi times the radius of the sun times the cosine of the latitude. And we have to use cosine here, which we wouldn't usually need to use. We have to use it because we're looking at a sphere, and depending on the latitude, circumference will actually change. Next, we're looking at the rotation speed. And speed, as some of you may know, is a scalar, which only shows magnitude and not direction. And you can find that through distance traveled divided by time traveled, and in this situation, it is the transit time. And we have a rotation period, which is essentially how long it takes our sun to make one full spin. Next slide, please. So here we have our equations and constants. Here I have the circumference equation, which is essentially just a raw equation used in math, but we have to modify it, and I'll tell you how we modified it. Since on HelioViewer we were only able to see half the sun, we just took the circumference and we divided it by 2, which, as you can see, we'll have the 2 cancel out in that equation, and we get pi times the radius of the sun times the cosine of the latitude. Speed is a simple physics equation, which is equal to your distance divided by time. Next, we have the radius of the sun in kilometers, which is 696,340, and that is important to help us find our circumference, and our rotation period, which you can find by taking your transit time and multiplying it by 2. Next slide.
All right, so now moving on to results. As you can see here, we have a histogram plotted. And the reason why we use the histogram is because it's commonly known to represent the values of numerical data to be compared and distributed. And so here we have a histogram of a rotational speed. And so as you can see, if you look on our histogram, you can see at the 3.29 mark, there's an outlier. And usually an outlier could result from slightly inaccurate tracking. And so that's the reason why we didn't use mean a part of our process. Instead, we use median, which is the center of all our data points. And so our median speed was 2.02 kilometers per second, and our standard deviation was 0.30 kilometers per second, which is the difference from median. Next slide, please. Here we have a rotational speed. And so looking at a rotational speed period, it's 24.33 days, which represents it takes about 24.33 days for the sun to orbit one time or spin one time. And the standard deviation was 2.59 days, which could be the difference of our median. And if you look on this graph here, there isn't really an outlier, a part of it, but we still use the same process so that we could keep it equivalized to each other. Next slide, please. Now moving on to our scatter plot. So after getting all our collected data, we placed it into the scatter plot. And a scatter plot is just a rotation period versus our latitude. So if you look on the latitude, you can see that we have a north pole and a south pole. And so we know that any poles from the northern side or the southern or any of our poles at all, they're usually spinning a lot slower compared to the poles or the sunspots that were tracked on the equator. Next slide, please. So here we see arrows pointing at our upper poles, and these poles lets us know or remind us that the spin of our sun is actually slower, or rotation is actually slower compared to the equator. Next slide, please. And the equator here, it's around the 22 mark, and with these sunspots that are tracked here, they were spinning a lot quicker compared to the other poles. Next slide, please. So it's basically, to sum everything up, the sun affects our planet in many ways. And so it's important to be learning and researching about the sun. And so when we were measuring the rotational period of the sun by tracking sunspots, we came out with the result that the median rotation speed we measured was 2.02 kilometers per second, and the median rotational period we measured was 24.33 days. Next slide, please. So thank you for listening. If there are any questions, we would love to answer them for you. We'd like to do some special thank yous to JD Armstrong, Ms. Kaiichi, our mentor Ellis, HiStar, the Institute for Astronomy, and the Solar Dynamics Observatory.
All right, well, thank you guys. That was very nice. We do have the ability to accept some questions from our viewing audience on YouTube. There will be a slight delay for that, so we're going to give them a little bit of time to do that. But while we're doing that, why don't I start it off with a question? You said that I believe it was 24 days, 24 point, how many days was it that you determined was the average rotational period?
Approximately 24.33 days.
Okay. Now, was that at the equator or was that at over all latitudes? And is there any sort of difference with latitude?
Yeah, so it was basically recorded from all data sets or all points of the sunspots that we recorded or tracked.
Okay, so it's from all of them.
It was the median.
Yeah.
Okay. Well, thank you. Let's see here. All right. Okay, we're not seeing any questions from our YouTube audience. Please remember that you are always welcome to ask questions, and we would really enjoy hearing from you. Next, we will go over to our comets group. And so let me get out of this. Going over to comets. And if I can hit the right button, we'll be in good business. All right. So the comets group, they were advised by Erica Bafunda. And Erica is a graduate student over at the University of Hawaii at Manoa. She's just fascinated, absolutely loves comets. The comet group is comprised of Zoe Fox. This is Zoe's first year attending HiStar, though Zoe Fox has attended HiStar before. This is not our first Zoe Fox, so kind of an interesting little point that while this is this Zoe Fox's first attendance to HiStar, we have had one before, and very good to have one back. Zoe's attending the Hawaii Technology Academy. And our other student is Kirill Esmiracle. He's a first-year student who attends Kihei Charter Schools here on Maui, and I will turn the time out. And last but not least, Rizame Bezik. And Rizame is a student over at Baldwin High School. So I will now turn the time over to our comet group.
Hello, everyone, and thank you for coming to our presentation. Today, we're going to be talking about investigation of the color and activity of long-period comets by the comet team with me, Kirill Smirka, Zoe Fox, and Renzeme Bazig, and our advisor is Erica Bafunda. Zoe, could you please continue?
So, some background information. Comets are small bodies that orbit the sun. The radius of a comet's nucleus, that's the solid part in the center excluding the tail, it's typically about 1 kilometer, which is about a 6,000th of the Earth's radius of the equator, so it's pretty small. They generally have an elliptical orbit, and there are 2 main types of comets, which we'll address in a second. Comets are mostly made of ice and dust, and that ice and dust is leftover loose material from the formation of the solar system. And comets go through a process called sublimation, which is where when a comet approaches the sun, the ice inside it turns into gas, and then gas and dust shoot out of the tail, and that creates shoot out of the comet, and that creates the dust tail that we see in those images. Next slide, please. So like I said, there are 2 types of comets, short period and long period. Short period comets have an orbit closer to the center of our solar system. You can see that in the diagram to the left. It shows the orbits of all the planets, and then that small white circle near the center, that's the orbit of the short period comet. And then long period comets have a much larger orbit. In the second diagram, you can see it's the same image of the solar system, just zoomed out really far, and that big huge ellipse is the long period comet's orbit. And we focused on long period comets for this project. Next slide, please. So long-period comets originate in the Oort cloud, which is a region of the solar system beyond Neptune, and you can see that in the second image. It's basically a big collection of leftover pieces from when the solar system was formed. They were too far away from the sun's gravitational field and too small to get turned into any planets or moons or anything. Next slide, please. The cool thing about long-period comets, or LPCs, is that since they're too far away from the sun to be affected by its heat, they're still in the same state they were in when the solar system formed. So by observing LPCs, we can gain more knowledge about what the solar system was like when it formed. In our project, we determined the magnitudes of 3 different LPCs in different filters to determine their colors and reflectivity. Next slide, please. So these are the 3 comets we studied: C2020T2, C2020R4, and C2019-03. In the top row are pictures of each comet, and in the second row are diagrams of their orbits. The third comet, C2019-03, that's the one I studied. It's an unbound comet, which means it's shaped more like a parabola than an ellipse. It doesn't really orbit the sun. And the last row is the comets perihelion and aphelion. The perihelion, or the little lowercase q, is the closest it gets to the sun, and the aphelion, or the uppercase q, is the furthest it gets from the sun. Again, with the third comet, since it doesn't really orbit the sun, it doesn't have an aphelion. And the next slide is for Curio.
Thank you, Zoe. Some of the data and resource we used during this project was the Las Cumbres Observatory and Gemini data. There we also attached a couple of logos. If you look to the top left, there's the LCO logo, and on the top left on the right side, there's the Gemini Observatory. We use different filters to determine where the energy light is, such as the G filter, R filter, I filter, and the Z filter. And sometimes we also use the B filter to find out about more information about the comets. And we also have to expose them a few times for a couple of seconds to understand how they work and how they are for light. Some of the websites we used, those are actually the same websites that are used by amateur and professional astronomers, such as Simbad, Panstar database, Aries.net. It was made by a Japanese man who made everything available to anyone who's around the world to learn more about comets. We also use GPL Horizons and GS9 to determine different pictures and focus on the data from the comets. We also used Excel spreadsheets. Next slide, please. Thank you. In creating images, we centered the comets, or we centered on the stars. If you look to the one on the left, the C2020R4, the student focused on the stars while the comet looks a little blurry. And if you look to the one in the middle, C2019R3, the student focused on the comet. And if you look a little closer to the stars, you can see that under different filters, the stars appear to be moving while the comet is still. And on the one to the right, C2020T2, the student focused on the comet too, while the stars look blurry. This all was centered manually, and there was about 4 pictures that each student had to make, and each of the photos or pictures that we had to do had to be put into a different filter manually, and it took quite a lot of time. Could you please move to another slide? Thank you. In data analysis for grid photometry, we use GS9, one of the websites I mentioned before, to measure the counts of our targets and reference their coordinates. We used 5 RSEC circular regions. RSEC is a measurement in astronomy. The little circle that surrounds the star is 5 RSECs. And we use them to find the coordinates and which region it is located. We also use the annulus region to measure the counts in the region and to find where the star is located too. We did the process for each image manually. If you look to the image on the left, the C2020T2, the reference, there is a star located on there. And if you look to the one on the right, C2020R4, in the annulus, the circle inside a circle, there is a reference star in the green, and to the bottom right, there's a comet in the red. Could you please move to the next slide? Thank you. In data analysis for photometry count, we use SIMBAD to find names and use PADSTAR to find database for magnitude and different filters. If you look to the picture on the top right, you will see a little window. That's what we had to find the star, each one manually, one by one, after we put in the coordinates. If you look at the bottom of the C2022 table, we use this counts in circle under each different filter that we have to find manually. We also counted the radius in arc seconds too, what size basically the circles were around the star. We also used the annulus, and we had to count manually the inner annulus and the outer annulus. We also were able to find with PanStar, we were able to find corrected magnitude and the magnitude image along with the magnitude error, also under each filter. Could you please move to the next slide? Thank you. In data analysis, for normalized spectral reflectivity, we used different data that we used from collecting the comets. There was also normalized reflectivity to find how asteroids and comets reflect different types of light when the sun's light is subtracted. Why it should be significant? Well, a comet colors help us to interfere composition and dash scattering effects after the comet leaves it behind. And the astronomers also for this can compare it to asteroid surfaces to understand where in the solar system the comet was formed. If you look to the images or the data tables on the top right, on the top bottom, or on the bottom right, we also put our own data that we collected from the comets and compared the two to see how the comet worked on the different filters throughout its time. Could you please move to the next slide? Riza, could you please continue?
Right. So while retrieving data, we had complications such as the SIMBAD website. It did not have a lot of filter information for our reference stars, so we had to go to the PanStars. We also had issues in collecting the correct data for the stars, or not receiving the correct coordinates for the star object. And one of our comets, C2020R4s, the colors didn't make sense, and it might be a bad calibration star. Next slide, please. The preliminary results, if you take a look at the data down below, we can compare our colors with the colors associated with the asteroids. We can determine what asteroid type our comet surface is most like. This will help us infer where the comet is from. So for comet T2 and O3, they have colors associated with the D-type asteroid surfaces. And R4, it has an unexpected reflectivity that we need to investigate. Next slide, please. Okay. So this is the light curve plot from the Yoshida comet webpage. The y-axis is the magnitude of the brightness, and the x-axis is the time. So the red line is the predicted brightness, and the black dots is data from different amateur telescopes. So for the comet C2019-03, if we plot the magnitude we found in our project on the comet's light curve graph, we can see that it falls right on the projected value. So this matches well with our results, and we can tell that we're using the photometry correctly. Next slide, please. So these main questions that relates to this project is, why does a comet appear in different colors, and what does a color mean, and how do we test this? So we hypothesize that the activity affects a comet's color, and we can test this by taking colors at different times in the comet's orbit and compare them. The rest of the questions are for future work. Next slide. Thank you.
Thank you.
Thank you. Does anyone have any questions?
We also wanted to say thank you to GD and Carolyn and Erica, our mentor, who helped in her own time to spare for a project. We also would like to thank UHISTAR sponsors and everyone who helped us on this project. Thank you so much. We also attached a small team photo of our Zoom on top left corner.
All right, wonderful. Thank you. Yeah. All right, wonderful. Thank you, guys. Virtual round of applause, I'm sure. We'll give a moment for the YouTube audience to catch up with us and ask any questions that they would like. And while we're doing that, so this unbound comet, does that mean that the comet just is passing through our solar system kind of like Oumuamua did, or what does it mean to be unbound?
It just means that it's not bound to our solar system. So it starts with it. It starts in the Oort cloud, and then it goes toward the sun, and then it just leaves. It doesn't come back to the sun.
Okay, so it kind of leaves. It's just kind of passing through our solar system, right?
Yes.
All right. Well, thank you. Let's see if there are any questions from the YouTube audience. I do not believe that there are. And so let's thank our speakers again, and we will move on to the next group. All righty. Probably want to start at the first slide. Wouldn't that be creative? All right. So this is our stellar group. And they have been investigating the age of 47 Tucan. Their mentors are Erica Sauchinech. Erica is a student, is considered an alumni of the High Star program. The only thing she ever missed was the 1 week program, but she was working with us as a high school student. She just recently graduated from the University of Hawaii at Manoa and has started the graduate program at the University of Austin, Texas, or University of Texas at Austin. Is that right, Erica? I'm hoping that's right. And the team members are Orion Teagarden. Orion is sort of an nth year. He's been to the program a few years before, and he comes here from Lahaina Luna High School. And a new recruit is Sydney Moss, who actually is not from Maui. He's from St. Louis, Missouri, and originally was attending more like, just to watch, and then started really getting into the research. And so he's considered a full attendee at this point. He attends Parkway Central Middle School in St. Louis, Missouri. And so I will turn the time over to Sydney and Orion.
Thank you. For our project today, as JD said, we are attempting to measure the age of the globular cluster 47 Tucan. To do this, we fit isochrones to a color magnitude diagram of 47 Tucan to give us a rough estimate of the age. It won't ever be exact using this. If you can switch the slides, Orion would like to carry on from there.
Okay, so we used, for some background research, we used a web page, an interactive web page titled Star in a Box. And so what Star in a Box is it's an interactive web page that pretty much lets us see what happens with the lifetimes of stars depending on how large they are. And it lets you see if they will turn into a white dwarf, if they'll turn into a black hole, all this stuff. And so you see that image on the right is what Star in the Box looks like. And so it's this graph that looks a lot like an HR graph, which is which we will talk about soon. So could you, yes.
All right, we've got about 2 slides of background knowledge, but I'll take the first one. Here we're going to be talking about a color magnitude diagram. This is a graph that charts the temperature and luminosity of a group of different stars. We can use this to, the way we're going to be using this, is we're going to match isochrones to it to, again, give us the rough estimate of the age of the star cluster. If you can see on the photo on the slide, the y-axis here is the luminosity compared to our star, and the x-axis here would be the surface temperature in degrees. As we go up, we will raise in luminosity. Here there's a little spot that says 1, and our star is in the middle. As we go up, we'll go up in luminosity. As we go over to the left, we will go up in temperature. So these supergiants, at least the red ones over here, are high in luminosity, but fairly low in temperature. If you can switch the slide, Ryan, would you like to take this?
Okay, so you've probably heard us mentioning isochrones. And so what an isochrone is it's a group of stars with a range of masses per star, and they're all the same age, and the age of each star is known to us. And so then what a globular cluster is it's a spherical cluster of stars. And the reason that it's the cluster looks like a sphere is because the stars are bound to each other by gravity. And the image here on the right is an image of an isochrone that we used. Next slide.
So method, it may have the least amount of words, but this is probably going to be our biggest and most important slide yet. So to get the actual information of the globular cluster 47 TUC or 47 Toucan, we used the Las Cumbres Observatory, specifically the node in South Africa. What the Las Cumbres Observatory is a collection of many different observatories with large telescopes inside. The South Africa node is the one that took photos of 47 Toucan for us. That is what the images, that was the image on the introduction slide that you saw. We took 3 different images, B, V, and R. That is blue, green, and red. V is green. I don't know why we didn't figure that out yet. We took those images and put them into APT. That is a program that looks at different stars and images, and we measured 1,880 of them that fit our parameters. It looked at, I believe, size, luminosity, and temperature. Correct me if I'm wrong, Orion?
I
That sound
think
right?
that sounds right, yes.
The APT will only select stars that are reasonably isolated enough to get a good measurement. So
Yes.
the criteria is really how measurable the star is.
So after that, we put them into, we put the data points into a Google Sheet. And we put them one in each line, and then we made a graph out of them using their built-in chart system. Then we also had a place where we got isochrones, which Orion very amazingly explained a moment ago, and we matched them up in the charts, and we went to see, okay, so which one matches here? We'll go a little bit more into that in our results slide. If you, JD, would you like to switch that? Ryan, you can pick up from here.
Okay, so while analyzing the data that we got, the closest that we thought we could get was 13 billion years old, but that was very subjective. And if you ask many different people with the same good intentions to look at the graphs from 9 billion years to 15 billion years, many of them would say that multiple graphs are the right ones. So our final answer was that about 9 to 15 billion years old is the age of the cluster, but we didn't go further than 15 billion years, so it could be older than that. We just didn't really go further than that. And so on the right, the top image is an image of the isochrone fit to 47 toucan. And I think that's about 13 billion years old. And then the bottom image is 3 billion years old. And you can see that the isochrone doesn't really match the blue scatter graph. And so that's kind of how we matched up the isochrones to our data of the actual cluster.
So here on the conclusion side, you can see 3 different graphs up here. The first one is the 9 billion year isochrone. That is the red line. That is all of the modeled out stars at 9 billion years old. That fit pretty well here. The blue dots are the measurements for the color magnitude diagram. And next to that, you can see the 15 billion year isochrone. And that too fits well enough that we could say, yeah, it might be 15 million years old. So it could be anywhere in that range. So if you look at the bottom image, that shows you isochrones. I believe that's, I think that's 9, 13, and 15. Ryan, is that correct?
Not totally sure, but around that range, yeah.
Yeah. So you can see that all of those isochrones look almost exactly the same. So when we place them on top of each other, we really cannot easily tell the difference. So we really don't know, we can't pinpoint the exact age of this globular cluster using isochrones. There are other methods that we did not get into that could much easier give us the age. JD, would you like to swap the slides? And Orion, I believe this one's yours.
Okay, so this is just our references for our the example of the color magnitude diagram. Also, if you would like to go to your browser and look up star in a box, I think it only works on a computer, not mobile, but I'm not totally sure. If you just Google star in the box, it should be the first link by the Los Crumbres Observatory. Yeah, it's pretty cool.
I'd like to thank JD Armstrong, Dr. Carolyn Chiacci, and Erica Watsonich, and the all of the other high star sponsors. They were a great help to us during this. All of them were able to answer some questions that we had while looking into this.
Okay, thank you. Any questions?
All right, well, thank you, gentlemen. We do have a couple of questions on the chat here. The first one is, well, what are stars?
Stars are, they're pretty much a lot of hydrogen and plasma that converts or it fuses hydrogen into helium, giving them all their energy. I don't know if I can say any more into that. Sid?
Yeah, so in the core of stars that are like our sun, they burn hydrogen into helium atoms. Once they really cannot do that anymore, they start swelling up and they get much larger, and eventually they can start burning helium into, I believe, oxygen and carbon. Eventually they get so large that, depending on the size, sometimes they can completely explode and then go back to a very small point and become a black hole, or they will just get really small, become a white dwarf, and eventually lose all of their heat.
All right. So it looks like you guys have some fans, and a round of applause on YouTube. If there are any more questions, I don't believe there are in YouTube just yet. So am I correct that the summary, one of the points that you are trying to make with your presentation is that this process of isochrone fitting kind of doesn't work very well if you're over, say, 9 billion years? Is that a good summary?
Yeah, that sounds about right. From what we saw, the highest isochrone we looked at was 15 billion years old, which is actually a lot longer than even the age of the universe. It's about, I think, 2 billion years longer. Don't quote me on that, but anywhere from about 9 to what we saw, 15, could be said they're the same stars. That's mainly because stars, at least during the main sequence, which if you go back to the color magnitude diagram, was the main line there. The color magnitude diagram. That's
the HR graph at the beginning, yeah.
There we go. So yeah, you see where it says main sequence? That's that big long swath there. Thank you. Those ones specifically age extremely slowly. They will take billions of years, and that's if they're pretty close to swelling up into giants and supergiants. That's when it starts to speed up, and they'll either become white dwarfs or not supermassive black holes. That's at the center of the galaxy. Just normal sized black holes. Lost my train of thought. Sorry. That's about how stars age and die. Do we have any other questions?
All right. Any other questions? Does not look like it. All right. Well, thank you. And we're getting some rounds of applause from the YouTube channel. I see Dr. Van Saders attended and seems to be impressed with your presentation. So great job, gentlemen.
Thank you. And hello. I believe you did the presentation. You did your presentation 2 days ago, if I'm not mistaken.
So you're giving a shout out to Dr. Van Saders.
Yes.
All right.
I believe 2 days ago, she gave a presentation on lifespan of stars and how they age. Thank you.
Yes. All right. So moving to the next group. The next group is the Dipper stars group. And here we go. So things that go bump in the night, shadows of planets and dust. This group was mentored by Dr. Eric Gaidos, Suchi Narayanan, and Rena Lee. I hope I got all the names pronounced correctly. And well, there was another student that was working with Holden. That other student is not able to be here today. So Holden Suzuki will be giving the entire presentation. Depending on your accountant, I think that Holden, you're like 3rd or 4th year high star. Is that about right?
Yeah, just about.
Yeah, just about. And you're attending Maui Waena Intermediate.
I'm gonna go to Maui High, but that's next year.
All right, so in the fall you'll be at Maui High.
Yeah.
All right. Okay, well, I will turn the time over to you.
So let's move on to our first slide. So what are we doing and why? So what we're doing is we're looking at Dipper stars or young stars that exhibit stochastic dimming, which basically just means aperiodic kind of random dimming. So we can learn a lot about early stages of stars and planetary formation from this kind of activity, because as stars mature, especially when they're young, they have like large rings of dust and other small objects like planetesimals, which are just small, like, well, not small, but about meter large rocks that will eventually collect into the planets, right? So we use light curves and spectral energy distributions to understand why the objects are dimming. So light curves are just a measurement of brightness at any given time. So if you'll take a look at our image, that is actually a light curve. So this is a light curve from a T Tauri star in the upper Scorpius cloud, exhibiting quasi-periodic dips, meaning that the dimming is periodic, but at varying depths. So yeah, this is a very interesting light curve, and this is an example of what we're doing. So yeah, let's move on. So you might be wondering, what are dipper stars? A type of young stellar object, YSO, generally 1 to 10 million years old. That's generally what they are. There's a couple different types, but this is the type we'll be looking at today. So this typically means that they have dust in their orbit. So the dust orbits them when they're forming planets, and they're forming as a star itself, and that results in the dimming that we are investigating. So the region we're looking at is within 1 astronomical unit of the star. Cosmic dust plays a really big part in the general way that planets and stars evolve. So let's move on. Okay, so there's a couple of properties we're going to be looking at. One is spectral energy distributions. This is basically saying how much of the light, or the energy of the light, is being distributed across every wavelength of light. So say like red has a lot of energy, but blue doesn't have a lot. We're going to be graphing that out. In this case, we're looking for infrared. About 7,000 angstroms is increased infrared flux in a star's SED, which is just their solar spectral energy distribution. This is usually caused by dust re-emitting sunlight that it's absorbed, and that makes it a longer wavelength. Other than that, we're also looking for ultraviolet excess, which is 50 to 4,000 angstroms. This is a signature of accretion or dismaterial falling into the star. So moving forward, we used a couple of different methods and to get our data. So first, we looked at alert systems like Gaia or Mars ZTF, which flag rapid and significant changes in the brightness or just light emitted by objects. So we chose to do objects with more than a 1 magnitude change. We checked Simbad to screen for whether they had a lot of just information about them. If they didn't, we wanted to use them because that means they're less well researched. Then we used Assassin to make a light curve. We could visualize the dipping with VOSA to generate SEDs. To move forward, we have our first object, Gaia DR2, 1974. We chose this because it only had 2 references, meaning that this object was not very well researched. It only had 1 identifier, showing that it really only turns up in 1 database. And we can prioritize this object for follow-up, which is really cool, using different telescopes or just cross-checking with other databases. Moving forward, we'll see its light curve, which is a very interesting part. So in this light curve, we see very obvious dimming. We have these little lines attached to each of the points. These are error bars. They basically say how much we could be off by, because it's very important to know that this isn't like exact. They could be off by about 0.2 to 0.1 direction. So yeah. Moving forward, we have its SED. So an SED is basically just showing how much energy is in each light, right? So basically what we're seeing here is that it's showing a normal black body curve until we get to the higher wavelengths where it's actually increasing, which means that it has an IR excess, which means that we are seeing a young stellar object, possibly, and that's really cool. Yeah, so this SED helps to show us that, you know, it has an IR and UV excess. So the dust in this plot is easily recognizable because as it's formed by the star, it's red as excess emissions, which we can see. So we're looking at the effective temperature as well, and that's about 2300 Kelvin, which means that this is likely a red dwarf, which is pretty interesting. Moving forward, we can look at our next object, IZ Vul, which is chosen because it only had 3 references, all of them dated back before the 2000s. And it had a clear dip in the light curve and had a really interesting SED. Moving forward, we can see the light curve. So it has very obvious aperiodic dipping, and that means that this is indeed a dipper star, and it's most likely a young stellar object. This object also fluctuates more than the other one. You can see on the sidebar that it has a much larger range of brightness, which is really interesting, and it also varies more within the error bars, which is cool. Moving forward, we can see that this object is also a very strange light SED. It's mostly just a slightly decreasing line, which is not what you would expect. This means that this object is an extreme form of accretion, which is really cool because this is kind of new and it's not what you regularly see. So moving on, we have knowledge that it's likely a G-type star, which is pretty cool. So in summary, we are investigating dipper stars and the dust around them, which allows us to analyze regions where the planets form. So looking at Gaia DR2, 1974, and IZ Vul using Simbad, Assassin, and the Virtual Observatory SED Analyzer, we found that both objects were in fact dipping and are both likely young stars undergoing accretion based on the UV and IR axis. After fitting the SEDs, we found that Gaia DR2, 1974, is likely an M dwarf or a red dwarf, and IZ Vul is a G-type star, which is usually a sun-like star. Thank you to J.D. Armstrong, Miss Caroline Fiichi, Suchi Narayanan, Rena Lee, Dr. Eric Gaidos, and the High Star sponsors. Any questions?
Sorry, I had to fight with my computer a little bit there to unmute myself. Thank you, Holden. We really appreciate that presentation. It was very nice. Let's see if we have any questions on the YouTube channel. We do have a great job, Holden, from one Suchi Narayanan. So thank you, Suchi. So how can you explain a little bit more about how the infrared excess shows that it's a young stellar object? I think I got a little lost on that.
I'm sorry, my internet's not doing so good right now. Yeah.
Try turning off your video. Sometimes that helps.
I am sorry, my internet.
Okay.
Well, could you restate the question if you asked one?
Yes. So how does can you explain a little bit more about how the infrared excess shows that it's a young stellar object? I'm not quite sure I followed that.
Okay. So basically, slide number 4 kind of shows this pretty well. Right above that, yep. So slide number 4 shows this pretty well. Younger stars will usually have planetary disks or protoplanetary disks where there's a lot of dust and just junk in there, right? That are waiting to form into planets, right? And so as the dust bounces, as the light bounces off this dust, it changes wavelength because it slows down. Well, not slows down, but it lengthens the wavelength of the light, and that'll lead to more infrared light, as demonstrated in the class 2, class 3, and class 1. So basically, because the dust is there, it'll make the light, well, not slower, but a longer wavelength, and that means that you're going to see a lot more infrared light than you normally would. If you're seeing a lot more UV, that normally means that it's got a large deal of accretion, and that the light is just heating up. Yeah.
All right, thank you, Holden. I must have missed that. Zoned out there for a sec.
No worries.
Do we have any other questions from the YouTube? Does not look like it. And so we're going to thank you, Holden, and great presentation.
Okay.
Up next is the active galactic nuclei group. I like to think of these as care and feeding of black holes. And so Gabe McKillop and Melanie Ream, they were both mentored by Anna Payne. Anna has been mentoring some high star students for a few years now, including Annika and Chetta, who you'll hear from shortly. Gabe McKillop, this is his second time attending the High Star program, and he will be attending Kinke Kaulike High School this fall. And Melanie is a first-year High Star participant and will be attending Maui High School. So I'll turn the time over to you and go ahead. Let's see here.
Thank you. So before we get into our presentation, we'll just go over some words to know because we'll be referencing them a lot. The first are AGNs, active galactic nuclei, which are supermassive black holes at the center of galaxies that emit more energy than normal. And Assassin 14KO is the specific AGN we are studying. And in order to study it, we did photometry, which is measuring how bright an object is in an image. And JS9 is a web-based program for measuring photometry that was really helpful in this process. The last term would be a light curve, which is a graph that shows the brightness of an object over a period of time.
All right. Before we start, what exactly is an AGN? Well, AGN stands for an active galactic nuclei. And what this is it's the center of a galaxy that emits more energy that we usually expected. This high energy environment is caused by a supermassive black hole in the center of the galaxy that is feeding off nearby material. These black holes often catch nearby material, causing them to orbit the surrounding black hole, creating what's called an accretion disk. So think of it as like a giant cosmic whirlpool. And the constant movement of all the space debris is causes it to get quite hot and shine really bright, and which we can then detect with telescopes.
So in order to study AGNs, astronomers create light curves, which as mentioned earlier, are graphs of the change in brightness of a celestial object over time. So if you take a look at the image at the top, that is the light curve of a normal AGN, which as you can see is very random. The spikes in brightness or the decreased spikes in brightness are very random and they're unpredictable. However, in the case of Assassin 14KO, which is pictured at the bottom, it has periodic spikes of light roughly every 100 days. And this makes it the first of its kind. We've never seen this before. A possible theory as to what might be causing this is that a star that is in orbit of Assassin 14KO is slowly being eaten every time it gets at its closest point in orbit. And this is possible because black holes have such forceful gravity that they are able to pull things into its orbit.
Great. Just a quick disclaimer. My internet connection isn't that great, so I'm going to have my camera remaining up for now. So since our galaxy that we're testing has been following the same trend over the past few years, we predict that we will see a sudden brightness in Assassin 14KO's light curve at near the end of August, early September of 2020. And then to test our hypothesis, we used a technique called aperture photometry to create light curves using data taken by Las Cumbres Observatory. We then took these images and did photometry on the galaxy, as well as 4 other reference stars in each image to calibrate our photometric data.
And again, all of our data was from Las Cumbres Observatory, which is a network of telescopes located all around the world. And our images were from 3 specific locations: Sutherland, South Africa, Siding Springs, Australia, and Cerritolo, Chile.
So to perform our photometry, we use this web-based software called JS9. And we use this website to record and measure the brightness of our galaxy. We also measure the brightness of four nearby reference stars in each image in order to calibrate our data. And since there's a lot of background interference from background stars, we also use a sky annulus to measure the local sky background and subtract it from the light incoming from Assassin 14KO, so we can get the most accurate reading for it.
And so in order to keep track of our data, we put everything in a spreadsheet. For this week, we focused specifically on B and V filtered photos, which are within the optical range of the electromagnetic spectrum. And so we put all of our counts in, including the AGN and also the 4 reference stars based on time period.
So after we got our photometric data and we plotted all on plotted them all on the sheet, we're ready to make a light curve. And so what this is showing is that this is showing the the B filter light curve of Assassin 14KO, and we detected a sudden increase of brightness, like expected, at the end of August, beginning of September 2020. As stated before, we were able to see a sudden increase of brightness near the beginning, and a gradual decrease in brightness for the next several weeks after the initial peak.
And so this is our V filtered light curve. And again, just confirming the fact that we did see a flare of sudden increase in brightness at the end of August, and then a more gradual decrease the weeks coming after.
So if we wish to continue our little study here, we can get a lot more data on this galaxy. We could work on more photometric data from other filters, as we only focus on 2 of them, which cover a wide variety of the electromagnetic spectrum. There's a question we can investigate, and that is whether the light curves look different in different filters. And we could use that newfound data and compare to previous years and help us predict when future flares will happen, and if there is a difference in future flares, so we can compare if it's the same as previous ones.
And then thank you. We will be taking questions, but a special thanks to our mentor, Anna Payne, the High Star Outreach Program, J.D. Armstrong, and Ms. Kaiji for all their hard work and help, lastly, Columbia Observatory, and then all the other High Star sponsors.
All right, thank you. Nice round of applause for you. And we'll be taking questions in the YouTube channel, if anyone has any. Okay, so this is a case where every now and then there's, am I right that this is a case where every now and then there's something coming along and feeding this black hole? Did I follow that correctly?
That's our theory, I guess, because it hasn't really been confirmed. At first, it was thought to be a supernova, but then obviously after the periodic repeatings, that was taken out. So yeah, the theory is that there's a star that is in orbit that is slowly being eaten every time.
So every time this star goes around, the black hole takes another bite out of it.
Yes, that is correct. or that's what we think.
Okay. All right, and we'll check the internet here for the YouTube channel for any other questions. And we do encourage questions from all of our audience that are watching over YouTube. Please feel free to ask. And our final group is our galaxy group. So the Galaxy group was mentored by Dr. Jenny Shi. Jenny is the professor of astronomy over at UH Maui College. And Aiden Chun. Aiden is a HiStar alumnus, and I think he attended for about 3 years, and he's now attending the University of Hawaii at Manoa. The HiStar, or the habitable zones of a galaxy group is comprised of Edward Deven and Annika Anchetta, and they, like I said, will be talking about habitable zones in a galaxy. All right, I'll turn the time over to you.
All right, thank you, JD. Okay, so here's our introduction. Like our solar system, galaxies have their own habitable zones, or places where metals that form terrestrial life and terrestrial planets and life are abundant. Our goal in this project is to observe these galaxies and figure out exactly where their habitable zones are. Next slide, please.
Okay, so we hypothesized that a star formation has a positive correlation to metallicity. And this is because with more star formation, more stars can emerge. And this means more opportunities for metals to form, affecting metallicity levels, which can ultimately create terrestrial planets as well as life.
So before we continue, here are some definitions. Metallicity is abundance of anything heavier than hydrogen and helium. In this case, oxygen and nitrogen are considered metals. There's also star formation. Could you go back, please? Thank you. Star formation rate, or SFR, which is the rate at which stars form in a galaxy measured in solar masses per year. And finally, the Spearman correlation coefficient, which is a number that measures the strength and direction of association between two variables.
Okay, so for our data, we took examples from the SDSS Mangus survey, which used fiber bundles to collect various sample data on thousands of galaxies within the universe. And the data used came in 3D arrays. The 2 dimensions were used for right ascension and declination, and the 3rd dimension was used for wavelength. And metallicity and star formation rate, otherwise known as SFR, was measured through comparing emission lines from O2, N2, and H alpha lines in the spectrum. Next slide, please.
So here's our procedure. First, we selected a face-on spiral galaxy. We selected face-on spiral galaxy candidates and downloaded their DataCube file from SDSS, and then opened the DataCube file on Google Colab. Then we made slices of the DataCube at the wavelengths of the desired emission lines and found the observed brightness of said emission lines. Using this, we calculated the metallicity and star formation rate, then made a graph and found the Spearman's correlation coefficient. We repeated this for all galaxies and compared the data finally.
Moving on, we used 2 equations mainly for this project. And the first one was to determine metallicity. And the main things you need to know in this equation is that O stands for oxygen, H stands for hydrogen, and R stands for log times N2 divided by O2. And to determine can you go black, please? Yeah. To determine solar formation rate, we use this equation, which is log times metallicity rate equals log times luminosity of the hydrogen alpha line minus 41.27. Next slide, please.
I just wanted to add the M. I'm pretty sure that stands for star formation rate.
Oh yeah.
Sorry.
Look that up. Yeah, sorry.
Okay. So here are our results. These are two galaxies that we used. As you can see, they're both face-on spiral galaxies. And going from left to right, they have corresponding graphs for metallicity, star formation rate, and metallicity versus star formation rate graph. The number above, P equals, that's the Spearman's correlation coefficient. It's basically a number that tells you how closely associated the data is. And as you can see, since it's higher, it's one of the higher values, around 0.7, it means that the data is closely associated with each other. Next slide, please.
So after analyzing the data, we discovered that there was a positive correlation between metallicity and the star formation rate in each of the observed galaxies. And a majority of the galaxies also had a high Spearman correlation coefficient above 0.2. However, on a side note, there were some observations that contained unreliable data, such as the low bar on the right of the graph. However, this did not affect the overall clarity too much when comparing metallicity and star formation rate in the project. Next slide, please.
In conclusion, our data supports our hypothesis. We concluded that in light of our results, there is a positive correlation between metallicity and star formation rate. Some possible next steps to take in this project include masking unreliable data points. The graphs shown before, they show correlation between metallicity and star formation rate, but they also take into account dark spots with little to no light. Additionally, we could analyze data from other types of galaxies, not just based on spirals, and subtract the continuum from emission lines. This continuum is on a spectrum, and it's caused by starlight. Next slide, please.
We'd like to give a special thanks to Aiden Shun, Dr. Shi, Jaden Hinkle, JD Armstrong, Caroline Kaichi, all the High Star sponsors, and everyone else who made this fun and interesting project possible, as well as for mentoring us on the topic of galaxies, coding in Python, and astronomy whatsoever. Next slide, please.
Thank you for listening. Are there any questions?
Sorry, I've got about 3 windows open and I have to always search for the one that has the mute button. Thank you very much to both of you. Sorry, I got a little off on slides, jumped the gun a little bit on you there. So do we have, all right, so we don't have any questions from YouTube yet. So do you have any idea of where the habitable zone for the Milky Way might be?
We didn't look at the Milky Way yet, but I can assume that it's somewhere where we are.
All right. Do we have any further questions? Jai is giving a shout out to Edward. I assume that you know Jai. And other than that, I think that we are we should wrap it up. And so this is going to conclude our program for today. We wanted to thank all of the presenters, the mentors, and of course the audience. We've appreciated your attendance. All right. Well, thank you. And
wait, there's one last question.
Oh, there's one last question. Someone snuck one in. I know the habitable zones of the star matter a lot, but why do habitable zones of galaxies matter? Oh, so the habitable zones of stars matter, but why do the habitable zones of galaxies matter?
Well, in the future sometime, like the long future, if we don't find any life here in the galaxy, we're probably going to start exploring other galaxies too. So like knowing, like dividing the galaxy down into parts where life can exist and life cannot exist can like help us well find life a lot faster than you usually would, because like galaxies span millions of light years. So it would be really hard to search each spot in the galaxy. So like cutting it down to a few spots would make it a lot easier.
Adding on to that, the habitable zone of galaxies can be applied to our own Milky Way as well. So we can study habitable zones in the Milky Way, like look at metallicity and star formation. And using that information, we can see whether stars in our own Milky Way are habitable as well. We don't need to just look outside galaxies, but we can use this information for our own galaxy as well.
All right. Well, thank you very much. If there are any other questions in YouTube, I will try to watch for those. I did want to correct one thing. I said that students were from Maui and the mainland. We also did, of course, have one attendee that is from Oahu, our very own Peyton Ikeda attends Mililani. So my apologies on that, Peyton. Of course, you know, just consider it us welcoming you as part of the Maui family. So thank you again to all of our presenters and our audience, and we will be signing off at this point unless somebody slips another question in at the last second. I guess not. All right, thank you and have a good evening.